introduction to symplectic geometry. It's a topic really in between math and physics. Like for physicists, it's like a topic which probably you know very well, like the Hamiltonian formalism of classical mechanics. And somehow, my viewpoint is a bit more from the mathematical perspective. So I really try to introduce the objects you've all seen, so these Poisson brackets and these, and these canonical transformations. I really try to understand where it really comes from, why we are interested in that, and what's somehow the conceptual viewpoint, not only somehow the coordinate-wise description. And we will use this kind of conceptual understanding in the second part of the lecture, which will be more about symplectic quotients and the Hamiltonian reduction, in which part we will better understand somehow this notion of symmetry and conserved quantities. And for mathematicians, why should we be interested in symplectic geometry? Well, there are several kinds of geometry. Like typically we distinguish between differential geometry, complex geometry, algebraic geometry, and symplectic geometry. So it's like one of the big families of geometries. It has like very nice properties, as we will see. Like it's very well behaved locally, but it has very complicated structure globally. It's a very active research area, actually, understanding these kind of global aspects of symplectic geometry. And maybe as an extra motivation, there are all these kind of links to physics. So it's really interesting to study this kind of geometry. Okay, so as I said, there will be two parts. The first part is kind of this gentle introduction to the whole topic. Actually, it could be a whole class. I mean, it could be for a whole semester. That's why, we will not see everything. I hope that you will get somehow the red thread through the story. And I will invite you to just dive into the topics by yourself if you want to get more details. And the second half of the lecture will be about this kind of a bit more advanced topic of symplectic quotients and these moment maps. Okay, so please don't hesitate to ask questions, to interrupt. I have written some references. There's this classical book by Lyon, Mathematical Methods in Classical Mechanics. Much more advanced is this McDuff-Solomon book. I would not recommend reading everything, but there are some chapters which are really introductory. And last year there was already a lecture course here. Donald Humans gave them, and the lecture notes are on the website of the MAPS event from last year. Okay, let's start. I wanted to start actually from an example. And from this example I want to derive somehow the big picture before getting to details. So even historically, like symplectic geometry really comes from physics, so it's actually really natural to start from physics. So let's take the best understood classical physical system, as we've already seen in Edward's lecture. It's the harmonic oscillator. So let's start from the physical system. Let's say the harmonic oscillator. So what is it? It's pretty much just a string. How's it called in English? It's something like this. Your axis, x, and you have some mass which can move. And when you write Newton's equation, Newton's law, you should get that mx, second derivative with respect to time, so this is the force, and the force will be proportional to minus x. K is some constant which depends on the string. Do you say string? No, do you say something else for this object? Which spring? Oh yeah, sorry, okay. So let's think about a spring, so it can move, and the farther you get, the more force you feel. It tries to get back to the initial condition, to the initial situation. So of course, you know this equation, you know the solution. It's kind of a sine or cosine function. So it gives kind of this wave equation. Not wave equation, but this wavy movement, periodic movement, and so somehow what at some point people observed is the following. So if you define the total energy, this will be one of the important kind of viewpoints is this viewpoint of conserved quantities. Of course, you know this is something which is very important. So let's call it H, total energy. So it will be the kinetic energy, and potential energy. So the kinetic energy is something like P squared over 2m. So what is P? P is mx dot. It's the momentum. And the potential energy should be something like kx squared over 2. Kx squared over 2 plus, because I have a minus sign here, so it's plus. Okay. So one thing you can check, it's very easy, check that if it's conserved, you can check that if you take the time derivative of h, you get 0. If you derive the first term, you get like p over m p dot. And the second term gives you like something like kx x dot. X dot, you can link it to p. And p dot, finally, you can link it to the Newton equation, and these two terms cancel out. Okay, so we have this conserved quantity. And then, somehow the first observation, let's say like the non-trivial observation, I would attribute it to Hamilton, but I'm not sure if this is historically exact, is the following. Actually, you can rewrite somehow Newton's law in a certain way. You can say, well, if you compute x dot, actually this is given by the partial derivative of h with respect to p. So we really treat h as a function in p and x. So you have function variables, you partially derive it with respect to p. Well, if you do this, so p and x are considered independent, k is just a constant, so you really get just p over m. P over m, and indeed P over m, by definition of P, is x dot. And if you compute P dot, this is actually simply given by dh over dx with a minus sign. So let's check. If I derive h with respect to x, so I will get kx, and on the other side, P dot is mx second dot, so this is minus kx. Oh yeah, that's a minus sign. That's right, that's a minus sign. So it works out. Well, it's an observation. But then you can say the following. Actually, if you consider the vector xp, and you take its time derivative, well then you get like x dot p dot. And then, actually, this is given actually by, well, the gradient of h. So the gradient of h is equals to d x to h to p. But you have to multiply it by a certain matrix, right? So x dot is given by p, so 0, 1, and p dot is given by minus 1, 0. So you have this kind of this interesting matrix appearing, and this matrix has a certain property. If you square it, 0, 1, minus 1, 0, you square it, what do you get?
Minus 1, minus 0.
Minus 1? Yeah, it's minus the identity. And this relation resembles something here. I mean, mathematicians know very well, but I mean, everybody knows very well. Something squared equals minus 1. It's like a complex number. And actually, it's similar to I squared equals minus 1. And actually, now we can explain this kind of strange term, symplectic. I always felt like it's a nice term, symplectic. But what does it actually mean? Well, actually, symplectic is Greek and means complex. I don't remember who invented it, but somehow the idea really was that symplectic geometry resembles a lot complex geometry, exactly because of this kind of reason. You have things whose squares to minus 1. So, like, let's say, like symplectic actually means complex. And actually, there are a lot of links between symplectic geometry and complex geometry, but it's not really the focus of the course. Would be a very interesting way to go, especially for those who know a little bit. It's something called scalar geometry, where you really get a strong, very strong link between these two objects. But like historically, that's where the name comes from. Okay, so this was like first observation. Let's go, well, before giving the second observation, let's go to a bit larger picture. So what do we do somehow in order to when we consider this object? I mean, so we have the gradient, or the gradient is a vector field, but we modify it. We have this kind of skew gradient. So this is kind of, skew gradient, but actually we'll always call it the symplectic gradient. Symplectic gradient. But so it's a vector field. Symplectic gradient. It is a vector field, but on what? It's a vector field on the space of x and p. I think for the physicist it's completely clear what it is. Maybe for the mathematician it's less clear, so it's something what we call the phase space. It's a vector field. It's a vector field on phase space. So maybe make some general comments on what phase space is. The idea is like you have a physical system. So there's an initial condition and you want to try to solve it. Solving means how does it evolve over time. And one idea which is pretty nice, I feel, is you write down the equation, you solve your stuff. Finally, the initial condition is not so important. You can somehow vary the initial conditions. And I mean, the solution scheme will not really change. It's at the very end that you really use the initial conditions. So what you can do is you can say, well, I will consider the space of all possible initial conditions, which is actually the same thing as the space of all possible, states, configurations of your system. And, well, this is the space of all possible things you could observe in your, in your system. And, well, you could say, well, why is this interesting? Well, first of all, it's not much more difficult to somehow solve all the system at once than just solving a single system. It's pretty much the same thing. But on this kind of big space, you have a lot of structure. One of these structures will be the symplectic structure. And also, conceptually, it's kind of really nice because, one configuration, which can be very complicated, of your system is just represented by one point in the space. And then this physical evolution, well, it's just some kind of trajectory in this phase space. So you just try to understand these trajectories. In particular, if you ask, how does a system infinitesimally change, well, this gives you these kind of vectors. If you do it for all the points, you get this vector field. So we'll see that kind of this infinitesimal evolution of a physical system is given by some symplectic gradient of some function. So it's like this a little bit, like phase space. This is something like space of all. Well, I think if I say configurations, then physicists are not happy because configurations is just the position space. Let's say space of all states, maybe. States of a given physical system. And then somehow, time evolution then corresponds to a trajectory in this phase space. Let's go to M. And infinitesimal evolution, infinitesimal evolution will correspond to some vector field, and actually it will be such a symplectic vector field. Okay. I'll go to one so far. Okay, now we can get the second observation, which for this time I'm pretty sure it's due to Liouville. It really says something about this phase space and the flow you have, like considering this time evolution. So you have an infinitesimal evolution, it's given by a vector field, and when you integrate this vector field, you get this kind of flow which comes from time evolution. Like if you, actually when I say trajectory, I again have this idea in mind that I have one system, but if I want to consider all systems at once, then actually it's not only a trajectory, it's actually a flow on M. Yeah. Flow. And what Liouville discovered is that this flow is volume preserving, at least for like closed physical systems. For closed systems, closed means something like there's not like energy incoming or outgoing. For closed systems, the flow in phase space preserves volumes, is volume preserving. So what happens, for example, in this harmonic oscillator? For the harmonic oscillator, our phase space is the space of x and p's. Well, let's say that x can be any real number, and p as well. So we have R2 for the harmonic oscillator. By the way, like in this picture, if you want to show how does like a typical movement look like, actually you will get kind of these elliptical things. These are the typical trajectories, like this, so on. But what does this kind of observation say is whenever you take a volume, if I take some box and I flow this box, it might get deformed over time. It might get, I mean, in this case probably it will not be like this, but it can actually deform. It will not be like this, but imagine a more complicated system. So this is like time evolution. It might get deformed, but the area in this case will stay the same. So why is this actually very natural? Why should we consider boxes in phase space? Well, you could say, actually you never really know the state of a physical system, right? If you measure it, there's always some uncertainty. So this kind of box, you can imagine, well, you have a system, you measured its velocity and its position, but actually you're just in some box because all your measurements are with some uncertainty. Okay, so you know the system up to some degree, and then this evolution is area or volume preserving. This means that you cannot really get more information out of the system just by waiting. Just wait, it will evolve, it will not give you more information. This makes complete sense, right? Especially if the system is closed, if there's not like energy coming in or energy losing. So this observation is very natural. Again, you will not get out more information just by doing nothing. As a, who said it, like no pain with no no gain without pain. Yeah?
No pain, no gain.
Yeah. Yeah. So you have to do something to get more information out of the system. But actually, it's much better. It's better, and I think this. I'm not sure if you has seen this. So it's much better. So in this phase space, which a priori can be very high dimensional, in this example it's just 2-dimensional, it's like a priori a very high dimensional space, this flow actually preserves not only the volume, it preserves actually areas, but not all areas, so certain 2-dimensional slices which will be preserved. The flow preserves areas of certain 2D slices. And these 2D slices, actually there's a notion, which you all know, is this notion of a conjugate variable. you have one variable, for example, position. It has an associated conjugate variable, which would be the momentum in this direction. And these two variables together, they form this kind of two-dimensional slice. And evolution will actually preserve the area of this two-dimensional slice. So there's a notion of conjugated, maybe just conjugate variables, forming these 2D slices. So we have something which is more better than a volume. And you can ask, yeah, mathematically, what is it? What is this kind of better structure giving this notion of conjugated variables and then gives kind of this notion of areas preserving, or certain areas which are preserved? And well, the answer somehow is that, there's this kind of symplectic structure. Mathematically, phase space has this kind of phase space, has a symplectic. I will define what it means, symplectic structure, which gives this notion of conjugated variables, and the structure is preserved under the physical evolution, and this means somehow that these areas, these slices are preserved. So let's say as a first approximation, let's say that symplectic structure is kind of a refined notion of volume. We will see later exactly what kind of this means, refined notion of volume. And so again, like this symplectic structure, it actually does several things. Like first of all, it gives you this notion of kind of symplectic gradient. It gives you actually the recipe how to do physical evolution on this phase space. And since it's preserved over time, it gives you this notion of conjugate variable and gives you this preservation of these areas, of these 2D slices. And also, as we will see, from the symplectic structure, you can derive a lot of other concepts, as for example, the Poisson structure and things like that. Okay, so this is kind of the big picture. We have some physical, some high-dimensional space, which has this kind of structure, symplectic structure, and then you can derive kind of the classical physics, say. But actually, if you dive more into the details, this kind of Hamiltonian formalism, it also appears more or less in quantum mechanics. So it's not only about classical physics here. Okay, so if you want, give you an exercise, you can try to do somehow the same analysis, like find the symplectic gradient, or like find a little bit what is the phase space. Yeah, it's a question of phase space, and like symplectic gradient for, well, what's the second complicated system? It's actually almost, later it's the pendulum. For the pendulum. Okay, so this I leave like for the break. If you want to try to see what's slightly changes, especially probably some of you remember this kind of differential equation of the pendulum, which is not, it's difficult to solve exactly, because you have something like the angle of theta double dot equals sine theta, something like this. And yeah, like if you redo this kind of analysis, you will find the Hamiltonian and you will see how this equation comes out somehow. Okay, so that's a good point for questions.
Could you repeat what you mean by 2D slices in that sense?
Yes. Okay, so you can imagine you have like a high-dimensional space. You have like a coordinate which points in one direction, say like x. Then you have like the momentum px, which goes in another direction. Then you have somehow a submanifold created by these two coordinates. And then inside, I mean, again, you take a box, and you cut it by the slice, so you get like a two-dimensional object which has some area. Then you let evolve everything. Again, you have a kind of deformed box. You have again like kind of the slice. It cuts this surface. I mean this thing again in some two-dimensional thing. And if you compare the two areas, then they are the same. Actually, it's pretty much something you know very well from quantum mechanics. It really resembles actually the Heisenberg uncertainty. You can learn maybe something about x, but then you will lose information about px. It's really this kind of phenomenon on a classical level. Okay, so after these kind of preliminaries, let's go to linear symplectic geometry. So for those who, the ultimate game, of course, is to do symplectic geometry on manifolds, curved spaces. But like the first thing before starting, like thinking about curved spaces, is what happens actually at one point. And in one point, very often things reduce to some linear algebra, and that's exactly the case here. So let's see how this linear algebra looks like. Okay, well, definitions and examples. Okay, so let's come back to the harmonic oscillator. What is actually the symplectic form? For the harmonic oscillator, well, we are in 2D. So in 2D, a volume is already an area. So we just have areas. So the symplectic form, I will always write it as omega, the symplectic form. It will be given by this dp wedge dx. So I think in Anton's lecture you have already seen kind of differential forms, but just to be sure that we know what this means, so it is, it's a differential form, differential two form. So what does it mean? It means that it takes as input two vectors, let's say v and w. So v and w are two vectors of R2, and it spits out a number. And let's take it in coordinates, so you have like v, well, let's say p vx, and s. And this symbol, dp dx, it means that you take the p coordinate of the first one, dp, and the x coordinate of the second one, and then you swap, but by swapping you take a minus sign. So now I take the x coordinate of the first one, and the p coordinate of the second. So this is how the rule, how you evaluate a differential form on vectors. So you can write it in a determinant way. It's the determinant of this matrix, dp, x. And maybe, I don't know, from high school or maybe university, you know that such kind of determinants, they can be interpreted as area. So it's the area of the parallelogram spanned by these two vectors. It's actually a signed area, right? Like it depends on if you switch the order of these two, then you get a minus sign. So this is a signed area. Signed area. Actually, without quotation marks, it's a signed area. Okay, so this happens in R2. So what happens now? Say what happens in Rn? well, you'll see actually why, but we have always to put an even number of dimensions. In R2n, I can consider you have coordinates pi, xi. I could put indices like below and above. The typical symplectic form, it's called the standard symplectic form, it's given by the sum of dpi much dxi. So really it's a bit like you treat R2n as R2 plus R2 plus R2 plus R2 and so on. And on every R2 you see this kind of area form. So to be sure you understand what happens in R4, if I take the omega standard and I apply it to two vectors, v and w, what do I get? Now I have coordinates. I mean, v would be a vector, v p1, v x1, v p2, v x2. Same for w. So what's the output? If I apply this omega standard to v and w, again you take two vectors, so it should spit out a number. What is this number?
P1, omega x1.
Omega x1, yes.
And then you have permutation. Yeah, then you have VP2.
Yes, v2, w x2.
Yeah, exactly. VP1, let me see. This is a plus then, right? And then you have...
Yes, plus, yes.
Okay. Then you have to exchange then VP1 omega x2 minus, right?
Minus VP1 omega x2?
Yes.
Okay, everybody is okay with that?
Oh.
Vx1.
Can we mix P1 with x2?
I'm a little bit confused with P1 and x2. I'm used to 1, 2, 3, 4. So, let me see. Wait.
You really think you should think about these pairs of variables. One pair is x1, P1.
Yeah.
One pair, and it's completely independent of all the rest.
So it's
So you have
Vx1.
yes,
And
x1 and P1, exactly.
And down below it's also Vx2 omega P2. Yeah.
P, no, V double. We go P2. Yes, exactly. And now actually, like in R4, it's not a determinant anymore. Determinant is in dimension 2 because determinant is an area. But in dimension 4, a determinant would be a volume, but the symplectic structure is somehow just an area form. But you add up somehow these two-dimensional area things. Yeah. Okay, so these are the examples, but well, what's the general definition? Questions on this? So what's the general definition? So let's take a vector space, finite dimensional, let's say over R, it's important over R. And yeah, so what's the symplectic form? Omega is a symplectic form on V if it has three properties. So it has to be bilinear, it has to be antisymmetric, and it has to be non-degenerate. Non-degenerate. Well, I'm not sure if you can read this. Non-degenerate. Okay, so what what are all these names, all these words, so bilinear and antisymmetric. So sometimes people would just say that omega is an element of this exterior derivative, the exterior power of V. Mathematicians have seen this symbol. So it means, well, omega is an object which takes vectors, like two vectors as an entry, but whenever you take like a sum of two vectors, a linear combination of vectors, you can somehow factor this out. So let's see, bilinear means, well, whenever you have like omega of, say, I don't know, lambda v plus mu w, comma, else v w u, then you can somehow say it's lambda omega v u plus mu omega w u. Antisymmetric means that whenever you exchange things, then you get a minus sign. Omega of w b is minus omega of w. So in particular, if you evaluate the symplectic form on the same vector twice, then you get 0. Non-degenerate means following. It means that whenever you fix one vector, like here, omega of v something, this is a map. It takes another vector and spits out a number. So this is actually now linear functional. So this should be actually an isomorphism. So it's an isomorphism between v and w and v star. Maybe I can write it a bit differently, like if I write it like this. So if this is 0 for all v, then this implies actually that w is 0. So it means like, if I give you any vector, there is always another vector such that the symplectic form evaluates to something which is not 0. Which actually means that for every variable, there is a conjugate variable. The conjugate variable is something which makes the symplectic form non-zero. Yeah, maybe I will write this of space. So this gives somehow the existence of conjugated variables. This. Conjugated variables come from here. Yeah. So this is a kind of an abstract definition. You should really bear in mind kind of these examples. Maybe one remark, this definition, it resembles a lot another definition. An object which is bilinear, non-degenerate, but symmetric, which is a metric. So you might say, well, actually symplectic geometry is, I mean, we're saying it's kind of a complex geometry, but it's also kind of a skew Riemannian geometry. And we will see throughout the lecture somehow some similarities between, well, some similarities, but also very kind of big differences between symplectic and Riemannian structures. So a remark, that's kind of a similarity to the notion of metric, or scalar product. Metric. So the scalar product, it's bilinear, symmetric. Well, actually, non-degenerate, typically what people say is it's like positive definite. It's kind of something, which is very similar to being non-degenerate. Okay, so from time to time we will compare what happens for symplectic structures and what happens for metrics. Like, for example, I mean, we will not give the definition right away, but we've seen that there's like a very important object in symplectic geometry, which is the symplectic gradient. And of course, you also have like the usual gradient, and we'll see also how they behave.
Excuse me.
Yes.
Maybe I'm really misremembering right now, but don't you need it also to be a closed form?
Not in the linear symplectic geometry.
Oh,
Because somehow, yeah, like in the linear world, everything is constant. But you're right, on manifolds there will be some more condition, which is the closeness. Yeah. Yes.
I'm a bit unsure what the role of the Hamiltonian is in this picture.
What is the what?
What the role of the Hamiltonian is in this picture. Like
In the picture here? Like in this big picture? Or?
this thing about the symplectic form. Like is like every symplectic form correspond to Hamiltonian or something?
No. It's more like once you have the symplectic form, like any phase space has a symplectic form. And then I said like the evolution, physical evolution, is the symplectic gradient. But symplectic gradient of what? Of some function. And the function you choose is the Hamiltonian. The Hamiltonian gives you physical evolution. But this is kind of independent choice from the symplectic structure. Okay, so now we have this kind of general definition. Let's see maybe two examples which are a bit more abstract. I mean, two more like examples which are not just this standard symplectic form. Actually, we will see at some point that in some sense there is no other example. Like in this linear symplectic world, the only symplectic structure which really exists is this standard symplectic structure. So if you really understand this one, it's actually enough. Right, let's see some other examples. So take vector space L, vector space. It will always be finite dimensional, always over R. And then consider V, direct sum between L and L star. L star are the linear functions, linear functionals on L. And I define omega as follows. So what should I give you? I should give you the rule which takes two vectors here and spits out a number. So a vector, since it's a direct sum, is something like this and this. So x and y are in L, and this psi and eta are in L star. And the rule I tell you is that you should apply psi to y, and you should subtract eta applied to x. Psi is a linear functional, so you can give it a vector and it spits out a number. You just subtract two numbers here. So this definition makes sense, and I claim that this is a symplectic form. Why is this true? Should we check? So is it bilinear? So if I, for example, have x1 plus x2, I would have x1 plus x2 here, but linear functionals are linear, so it splits up. If I have x, it's like psi1 plus psi2, again, it splits up. Same for y and eta. Addition, no problem. If I take like now a scalar product, I take 2x, for example. Well, again, 2x, 2 will factor out, 2 psi as well. The formula is kind of bilinear. You can check. Linear. Check. Antisymmetry. Antisymmetry is easy, right? You exchange the two entries. So what is x becomes y, what is psi becomes eta. And because of this minus sign, you exactly get antisymmetry. Antisymmetry, okay. And what always has some more work is this non-degeneracy. So what should we check? We should check like if I fix x and psi, there is some y and eta such that this expression is non-zero. Okay? How can I do that? X and psi fixed and non-zero. Non-zero. How can I find y eta such that omega is non-zero? X
eta equal minus dual variable to x, and let's say y equal dual variable to psi.
Eta equals minus psi.
No, minus dual variable to x, so that would give 1 as.
Okay, that's such that this gives you 1, yes. But if you do the same here, then you have 1 minus 1, you get 0.
No, so 1 is minus, this can do without minus.
Say it again.
So let's say eta minus dual to x and y equal just dual to psi. Or like.
Oh, you want to take the dual and some kind of the anti-dual. So you have like a 1 minus minus 1.
Yeah.
Okay. Okay. I would have said like
Or you can just take 1.
you can just take 0, for example.
Yeah.
For y you take 0, so psi of 0 is 0, and then for eta you take something which pairs something which is non-zero, which always exists. I mean, when x is non-zero. When x is non-zero, like if you have a non-zero vector, there's always a linear functional which evaluates to 1, for example. Like just taking a scalar product and taking a scalar product with itself. Okay, so I will. It's kind of not completely easy, but this is the reasoning. Like you really have to use somehow that the pairing between the dual of a vector space and the vector space itself is non-degenerate. Okay, then I have the second exercise, which is pretty similar in spirit. Like an example, I let you prove that it is actually a symplectic form. And this example is actually comes from this world of complex geometry. And now I take a vector space, example, exercise. And now I take a vector space over C. And I consider a Hermitian form, H, V, to C, Hermitian form. What does it mean? It means it's bilinear. And it has kind of this property that hxy equals hyx r. Whenever you change variables, you conjugate. And we have something like hxx. hxx by this property is real, so you want it to be positive. Real. Okay, so it's a Hermitian form, and what you should show is that the imaginary part of H is a symplectic form. So you take two vectors, you evaluate H, you get a complex number, take its imaginary part, so you get a real number. This should be a symplectic form. Okay, so after kind of the definition, some examples, I would like to try to maybe link this to what probably you're more used to see, which are coordinates. So what is kind of the matrix viewpoint of this matrix viewpoint? So in order to get a matrix out of this kind of bilinear form, this vector structure, you need to fix some bases. So we have B is this vector space with bases I. So I can consider this kind of matrix in basis E of W. It's just this collection of numbers, omega, E, I, and J. I and J vary over. I varies, let's say, from 1 to n, if n is the dimension of B. So I collect all these numbers, I put them into a matrix. And then, if I want actually to write, like, what is omega evaluated at two vectors? Oh, by the way, actually, do you really see the difference between my W and my omega? So what you should do is, you can take formula, I mean, in coordinates, this formula looks like this. Like you have omega ij. You should take vi wj, right? Sum over ij. And well, this you can write as like V transpose this matrix. Actually, I will pretty always write it as omega. So this I will write it as V omega W. Where here I really see omega as this matrix. Okay, so this again pretty much looks like a scalar product, right? When you have a scalar product, you also associate a matrix, and whenever you want to evaluate a scalar product into vectors, you do pretty much the same thing. So, I mean, this kind of recipe is actually something which is very general for any kind of bilinear form. If it's symmetric, you get the metric. If it's antisymmetric, you get this symplectic form. Okay, so what are the properties of this matrix? So we should try to translate the properties of omega into this matrix. So somehow the fact that omega is bilinear actually means that I can somehow write this matrix. Makes sense to write this matrix. So what does it mean that omega is antisymmetric? It means that this matrix is antisymmetric, or skew symmetric. It means that when you transpose it, you get minus. Omega transpose is minus omega. Okay, so this is like this antisymmetry. Like if I exchange I and j, you get a minus sign. And what does it mean to be non-degenerate? Exactly, yeah. So the determinant of omega is non-zero. This is non-degenerate. Actually, I pretty much agree that this viewpoint may be much more convenient than this kind of abstract definition, because now we can just say, okay, a symplectic form, it's an antisymmetric matrix with non-zero determinant. And we know how this kind of object evaluates on two vectors. We just plug in this kind of formula. Okay? Maybe this makes it more, I don't know, human, more easy to grasp what it is. And especially we can now derive like one of the first properties, very important property of symplectic structures, which is that whenever you have symplectic structures, you are on even dimensions. And this you can just get from this. You can just get it from these last 2 points. We have a matrix which is antisymmetric and of non-zero determinant. This actually implies that the dimension is even. First proposition. So, when I have a symplectic vector space, then this implies that the dimension of V is even. I mean, from a conceptual viewpoint, somehow this is not surprising, because I said like symplectic structure, it gives you to any variable, it gives you a conjugate variable. And actually the conjugate of the conjugate is the variable itself, so actually all the variables come in pairs. So the dimension should be even. But like if you want to prove it, like, let's prove. Well, let's say like you take the matrix associated to omega, so we know that it's non-zero determinant. And now the determinant of a matrix does not change when you transpose it. Determinant omega transpose, but we know that omega transpose equals omega. And then if you have the determinant with some factor, then you can pull out this factor, but to the power of the dimension. Minus 1 to the power of dimension of V times the determinant omega. And now if you compare this to this, since it's non-zero, this factor has to be 1, so the dimension has to be even. This is my dimension. Nice, isn't it? Okay, and just before going to the break, the break is at 10, right?
Yeah.
Yeah. Okay. But before that, let's see the second kind of important property, which somehow justifies kind of our first approximation, which was a symplectic form is kind of a refined volume form. So now, if the dimension of the vector space is n, we know that it is even. Let's call it n. And we have the symplectic form. Then we consider omega, which omega n times. So we have a two form n times. We have a 2n form. And this is actually a volume form. Is a volume. So what is a volume form? Like if you have a vector space of dimension m, then the volume form is a differential M form, which is non-zero. So what does this proposition mean? It means that whenever you have a symplectic form, you can imply the notion of a volume. It's really in the sense that symplectic form is actually better somehow than the volume form. And whenever you have like transformations which preserve omega, which preserve the symplectic form, it automatically will preserve this volume form. Maybe to be really concrete, let's see what happens, like for example, in dimension 2. In dimension 2 it's already done. Let's consider R4. So if I have omega dp1 dx1 plus dp2 wedge dx2, how would you compute, board, how would you compute omega wedge omega? I'm sure to what extent you're familiar with kind of these exterior products. So the exterior product, it's pretty much like a usual product, so you have like associativity, but the only kind of important thing is that it behaves kind of like a fermion. Whenever you want to switch two elements, you get a minus sign. And by this, whenever you have twice the same object multiplied together, then you get 0. So if I compute omega wedge omega, then you should imagine this wedge itself. So you will get the first term, which is something like dp1 wedge dx1 wedge dp1 wedge dx1. But this is 0 because you have twice dp1, for example. This is 0. Then you get another term which is dp1 wedge dx1 wedge, and then you take the second half, dp2 wedge dx2. So this is somehow, like you really have to imagine it's kind of an associativity, like you have two times these terms, so you take the first with the first with the second with the first, so you get this term dp2 wedge dx2 wedge dp1 wedge dx1, and you get the last term, which is something like dp2 dx2 dp2 dx2, which again is 0 because we have twice the same coordinate. And what do we do with these two? Well, you can try to shuffle things in order to get the same object. Like for example, if I exchange x2 with p1, I get a minus sign. I can exchange again, I get another minus sign, so I have a plus sign. So I have like put x2 to the end, and then I can take my p2, change it again and again to put it at this place. So in total I have like 4 minus signs, so you get a plus sign. So this is actually twice dp1 wedge dx1 wedge dp2 wedge dx2. And kind of like taking the wedge product of all the coordinates is exactly the volume form. This is volume form. And actually in general, like in order to get the standard volume form, somehow, the standard volume form, which is kind of this product dpi, well, I'll write it. It's like dp1 wedge dx1 wedge dp2 and so on, and you go on to dxn. So this is the standard volume form. If you want to get this standard volume form from the standard symplectic form, what you should do is take omega st wedge omega st n times. But actually when you do this, as we see, you get this kind of factor. In general, the factor will be n factorial. And very often, actually, people just write it like this. They just write it like this. Maybe sometimes with a wedge here, but yeah. So having the symplectic form, taking it to the power of n, kind of having this kind of factor, sometimes we use in order to get the standard volume form. In general, you get this volume. Okay, so I think we'll make a break until...
Alex, I think I misinformed you. Actually, the break is at 10:30.
Ah, okay.
We could take a break now, but I think the coffee won't
It's
be...
not worth it. No, then it's good. It's good. Maybe then it's time for questions.
One thing actually, if the wedge is anti-symmetric,
Yes.
why don't we get 0 when we wedge omega with itself already? Because we could just exchange
Good
omega.
point. So I mean, you see somehow what happens. I mean, it's like on elementary objects. This is 0. But here you have kind of composite things, right? You have like dx plus dp. If you wedge this with itself, dx wedge dp plus dp. Well, then of course this is 0 and this is 0, but you have the cross terms. Well, actually here, well, this is actually 0 as well. This is 0 as well because, yeah, this is 0 as well. So in general, I think the rule is if you wedge a form of itself which is of degree odd, then I think you get 0. But omega is of degree 2. So when you wedge it with itself, actually, that's a very good question. Like here we have two objects which are almost the same. Then you like somehow you do some operations, and it really depends. If you get a minus sign at the end, it will cancel out. If you get a plus sign, you get something. And like if the form is of odd degree, then you get a minus sign, so everything cancels out. And if it's of even degree, then something happens.
The problem with that example that you gave, the second example, is that it's a one form. One form wedged with itself is always 0.
Yeah, it's the same for a 3 form, I think. It's the same for a 3 form, isn't it? Yeah.
The alpha wedge beta is...
Yeah, exactly. Yeah, exactly. Like alpha wedge beta is minus 1 degree alpha beta beta wedge alpha. Yes, I think so. Yes. Okay. Other questions? Okay, so we're almost done with like linear stuff. It's not that interesting. I mean, it is interesting. More interesting stuff happens in manifolds. Just I want to give some vocabulary and kind of the main theorem in this part, which says that actually, basically, the only example is the standard form. Okay, so second part, okay, so once, when you're in like linear algebra and you have kind of bilinear form, like typically what you do, for example, when you have a metric, and you have a scalar product, well, it's interesting to consider orthogonal complements. So there's a definition very similar in the symplectic world. So whenever you have a subspace, subvector space, then there's this notion of an orthogonal, the symplectic orthogonal, which is the space of all vectors such that whenever you pair them with vectors in U, you get 0 for all vectors in U. Symplectic orthogonal. Symplectic orthogonal. And it has many properties similar to the orthogonal you know. So it's, for example, like easy properties is like whenever you do it twice, you take the orthogonal of the orthogonal, U itself. And another thing which is true, first point and the second point. Second point is if you compute the dimension of U plus the dimension U orthogonal, this is the dimension of B. So you really get the impression that actually it's the same as it's the same object as for metric, but no, there's a big difference. There are big differences. You have some red. Yes. Attention. It's kind of different. It's different to usual orthogonal complement. Why? Well, for example, if I take a line, U L line, like a one-dimensional subspace. Well, if you take its orthogonal, then actually L is a subset of contains it is contained in its orthogonal. Why? Well, because whenever you evaluate a vector on itself, it's 0, because omega is antisymmetric. So if I take a vector, say x, which generates the line, and if you look at this definition, well, then x should appear in the orthogonal, because omega x is 0. Since omega of x is 0. Yeah, actually for all x. In particular, for an x in L. Okay. So you have kind of this situation where orthogonals can actually contain, contain in your own orthogonal, which is a bit strange. And so there's kind of this definition, which is kind of important. Like we will say that U is called Lagrangian. So you should not mix this up with like the Lagrangian formalism of classical mechanics. It's different. Lagrangian if U equals U orthogonal. So this might seem really strange. I mean, you have an object which is its own orthogonal. What does it mean? What is this? Yeah, what does it imply in particular? Like first thing, what we can say is that the dimension of a Lagrangian is always half the dimension of the total space. Property, like if you have U inside of V and U Lagrangian. Well, we have already seen that the dimension of V is even. So the dimension of U will be 1/2 the dimension of V. This comes actually from the first line there. Right? Dimension of V equals dimension of U plus dimension of U. Orthogonal, if U orthogonal is U, it's immediately the dimension of U is 1/2 dimension of V. Okay, look, let's see an example. So if I take, as always, R2n, the standard symplectic form, and as U, well actually, because of Lagrangian, I will call it L actually. L, I take the span of, let's say, all the xi coordinates. Then I claim that this is a Lagrangian. You can check whenever you take. Yeah. I mean, some of the rule is if you want to build a Lagrangian, like you should always take, like you imagine you have all these pairs of conjugate variables, you should just pick one out of them, never two. Because if you take two of a pair of conjugate variables, well, then it means that omega between these two variables is non-zero. And, oh yeah, this is actually something I have not said. Equivalently, this is equivalent actually to saying that if you restrict omega to U, you get 0. It means like whenever you apply omega to two vectors which belong to U, you always get 0. So this is why whenever you take two elements which are conjugate, so conjugate means that the omega evaluated at these two is non-zero. So you will not be Lagrangian. But if you pick exactly one out of every pair of conjugate variables, you get a Lagrangian subspace. So this is Lagrangian, or if I take the span of all pi, same, this is all Lagrangian. Okay, so I remember when I first saw this definition, I know maybe in my second master year or something, like it was like a math course on this, and I asked myself like, why is this interesting? Why do we care about Lagrangians? And then I asked I think I did not ask the professor, it was too intimidating, but I asked like the person who did the exercise class, and he was like really a bit embarrassed, like, yeah, it's an object, we consider it's interesting. Wow. So that's like the question I want to ask you, and I think there is actually a good answer. So why are Lagrangians interesting? We can discuss it at some point. I really think it's good actually to think about yourself, and I give you a hint. You should think not only classically, think about quantum mechanics. The second philosophical question today. Any questions so far, apart from this one? So then, to finish the first half, let's speak about this kind of classification. So in order to speak about classification, we should speak about isomorphisms. So whenever you have a kind of mathematical structure...
Question.
Oh, sorry.
I wanted to ask if it's related to boundary conditions, for example. Can you think of boundary conditions as Lagrangian submanifolds? Fixing X, like Neumann or Dirichlet, something like that.
By boundary conditions, like subspaces, or...
Yeah, like for some mechanical problem.
Yes, somehow. Yeah, there is something like...
I would have guessed something with symmetry.
Let's think about it. Maybe after the break, or like at some point we can discuss it. Apart from this, any other questions? Yes.
Sorry, I don't know whether this question is like well defined, but so in I think in classical mechanics we have canonical transformation, which will like change another set of conjugate variables. So would that be referred to like there exists more than one, like there is no unique this omega form on the vector space? Or?
Not really. I mean, we'll see what actually, I mean, that's a very good point actually to go on. What is a canonical transformation? By definition, a canonical transformation preserves omega. But it might, of course, change your coordinates. And in particular, actually, I always, like, you get really the feeling like when you have a variable, there's a unique conjugate variable. But that's actually not true. You can always, I mean, it's not unique. It's like any variable such that when you evaluate this form on these two, you get something which is non-zero. Typically, you would normalize it to be 1, but actually, when you have like omega of, I don't know, x and p, by definition this is 1, but if instead of p, I take p plus x, for example, it's also 1. So actually, conjugate variables are not really unique, but still it gives you like an idea of, but by the way, like if you take the two-dimensional slice of x and p, I said like kind of the evolution preserves this area, but if you take x and p plus x, it will give you another slice, but again, this area will be preserved. So conjugate variables are not unique, but all these kind of slices, these areas are all preserved.
Thank you.
Okay, so for this question, somehow let's see. I mean, canonical transformation is really in this kind of spirit of manifolds. So let's say what is like a good map. So when you have two vector spaces, which are symplectic, a map between them. So this is called a symplectomorphism. Well, actually, let's stick to this terminology. Mathematically, what you can do with a form, you can pull it back. So if the pullback of this form equals omega. So in physical terms, it means somehow that, well, once you identify somehow V with W using F, then the difference between these two objects It's just kind of a coordinate change. Physically, this means like omega equals omega up to coordinate change. And in particular, we will actually, basically, I mean, we are much interested in transformations of the vector space to itself. So there's kind of this definition of a symplectic group, SPVW. It's like the space of all linear transformations. So it's the space of all matrices, invertible, GLV, such that the omega, like this form is preserved. And actually, how does a matrix act on the form? Well, it's kind of this, it's the same formula as for a scalar product. It's M omega omega transpose, so this has to be omega. Okay, so this is called the symplectic group. Maybe for those who know a bit about classification of Lie groups, these symplectic groups, this is type C, like type A is SL, type B and D is SO, orthogonal groups, and type C is symplectic groups. So somehow they are, they play somehow an important role in the classification, and that's actually maybe why, I mean, you could say, well, there's like symplectic geometry, Riemannian geometry, complex geometry. Why should it end there? Maybe there's geometry of type X, Y, Z, and so on. But somehow, once you have the classification of Lie groups, somehow Lie groups define somehow what kind of geometry you can look at. So SO gives you somehow Riemannian geometries, while SL, which is just kind of volume-preserving geometry. And yeah, and so one big class is this symplectic geometry. It really comes somehow from the classification. Okay, and then we can state this theorem. Well, I'm not sure if it's really due to Darboux. I mean, Darboux is really the manifold case, but let's say it's like the linear Darboux theorem. Well, it says the following: whenever you have any finite dimensional symplectic vector space, then this is always symplectomorphic. To R to N and the standard symplectic form, where 2n is the dimension, of course, of V. Somehow, in math terms, in more like physics terms, in other words, it means that you can always find a basis, you can always change your basis. This is the basis EI Fi of W, of V, such that the associated matrix, like when you write the matrix of this symplectic form in this basis, you see somehow the standard symplectic form, which means that omega of EI, EJ, 0, same pair F prime Fj, and omega of EI, Fj equals delta Ij. So again, this kind of relations pretty much like the canonical commutation relations in quantum mechanics. This again is maybe like one reason why this formulation of classical mechanics in this way is so important, because somehow you can almost read off quantum mechanics. Like quantization mathematically is described by kind of a map from symplectic world to some Hilbert space world. And these really reflect this canonical commutation relations. Okay, is the statement clear? Somehow, if you want to think about the symplectic vector space, you can really just think about the standard symplectic form. And since we have some minutes left, I can give a proof sketch, because it's actually really kind of easy to prove. So we want to build kind of a basis. We start from this data, some symplectic form, and we want to build this basis. So let's start with the first vector. We choose E1, any vector, but it has to be non-zero. Any non-zero vector. And somehow what I will do it step by step. I want to find one conjugate variable. And once I have done this, somehow using the symplectic orthogonal, I can somehow cut this kind of two-dimensional space I found off from the rest, and then I can do some kind of induction. So let's find a variable. So again, it's not unique, but it exists. Find a conjugate variable f1 to e1. So yeah. So we know that. We know that there is, let's say, f1 prime in V, such that omega of e1 and f1 prime is non-zero. So why do we know this? Exactly. So this really, you see how, why it's really important to have kind of this technical assumption. This is exactly by non-degeneracy. It says whenever you have a non-zero vector, you can find another vector which pairs to not something non-zero, and then you can, of course, just renormalize. Probably something like f1 should be f1 prime divided by this omega e1 f1 prime. And then it pairs to 1. That's what we want. We want e1 f1 to be 1. Once you have this, then you can say we take the span of these two, e1 f1. It's actually symplectic symplectic subvector space, symplectic subspace. And actually, when you have a symplectic subspace, this means actually that V is U plus U orthogonal. And this is also symplectic. It's also symplectic. And then you really can use induction of the dimension of U. Orthogonal is the dimension of V minus 2, so we can use induction. Use induction. Again, you start with any vector, non-zero, you find somehow its partner, you split it somehow off, you split it off from the rest, and the rest you do induction. Like if you have a basis here, you just add these two vectors, you get just basis. And somehow the definition of this orthogonal, why is this so important? Because it means that whenever you pair any vector here with a vector here, you get 0. Somehow it's one of the things we want. That's why it's important to take this symplectic orthogonal. Okay, questions? Yeah.
So how can this be a direct sum? Because certainly E1, for example, is in both U and U complement, right?
No. U complement is the set of vectors which pair to 0 with all vectors.
Oh, yeah, I see.
So yeah, if like your vector space is one-dimensional, it will contain itself, but it's not true in general. That's,
Okay, yeah.
Other questions? Yes.
So all the symplectic linear spaces are that have the same dimension are symplectomorphic.
Yes. Yeah, I agree. Yeah. What we'll see later on is it's even stronger. Like when you do geometry on a manifold, you should always like ask kind of 3 questions, like what happens at one point. That's what we've just done here. Then you should ask what happens in a chart, like what mathematicians call locally. Actually, I think physicists, when they say local, they mean actually at one point. So, like what we've done here is local, somehow, but I mean, yeah. So you should ask what happens at one point, what happens in a chart, and what happens globally. So this linear Darboutium says like whenever you have a symplectic structure on a manifold, you can like choose your coordinates such that in one point you see the standard symplectic structure. But actually what we will see is much more complicated. The Darboux theorem will tell you that even like in the mathematical sense locally, like in a small neighborhood of a point, you can choose your coordinates in a way that you only see the standard symplectic structure. That's what I say, like locally symplectic structures are kind of very, very well behaved. They all look the same. Locally, there's nothing really interesting which happens. And that's, for example, this is a difference to like metrics. Metrics locally can behave very differently. Why? Curvature, exactly. That's an invariant, which is curvature. And like these kind of local invariants you don't have in symplectic geometry. And that's why the global study of symplectic manifolds is very difficult, because the only difference between symplectic manifolds happens somehow on this global level. And yeah, since we have like 1 minute left, maybe some overview. I mean, there are many kind of very natural questions in symplectic geometry which are still open. Well, we'll see that if you have a symplectic structure on a manifold, of course the manifold has to be even dimension. But is it true that like every even dimensional manifold has a symplectic structure? So actually, it's easy to find counterexamples. So the answer is no. But given like a specific manifold of dimension even dimension, is it symplectic? This is a very hard question. No hard answers, and even like if you know that there is one symplectic structure, you can ask like maybe there are others. Can you classify all possible symplectic structures on a given manifold? This is complicated, and even this might be the first time I saw this, I did not understand, but even for R2n, this question is open. Because, I mean, here we get the impression, well, there is a unique symplectic structure, but what we do here is really, we are in this linear world, so we actually just look at constant symplectic structures. So this theorem tells you, like, on R2n, the only constant symplectic structure is the standard one, but there might be symplectic structures which are not constant, which vary, which depend on the point, and I think this is still an open question. I think the conjecture is that there is only this one, there's only the standard one, but I think it's open. Are there exotic symplectic structures on R2n? People don't know. So yeah, that's why it's a field which is very much active. There are many very natural questions which are still open, but there also are actually really like recent breakthroughs like concerning like symplectic capacities, some kind of global invariants, which allow sometimes to say, well, this manifold and this manifold, they are two different symplectic manifolds because this or that invariant is different. This is kind of recent. Probably will not touch on this, but just to give you a flavor of what this field is about. Okay, I think this is, yeah.
Just like on the question of Lagrangians, so the way I understood it was like omega is some kind of formalism of this idea that you've got these 2D slices in your phase space that are invariant in the flow.
Yes.
And somehow that's like saying that you can't generate information or something. So it is like a Lagrangian subspace is like your maximal subspace of no information because...
very good, very good. Yes, this is, I mean, yeah. This is more or less the thing. What kind of information you can be sure to know. You spoiled it. Okay, then let's make a break until 11. So what is a symplectic form? Omega is a symplectic form. And if following conditions hold, so it has to be again antisymmetric and bilinear, so we can shortly say it like this: omega is an element of this second. This is somehow this is the space of differential two forms. So it is like bilinear and antisymmetric at every point. And it's somehow important, like it can vary from point to point. It's somehow a sect, like you can imagine it somehow like your manifold consists of points. At every point you have kind of a linear space, which is the space of two forms. This gives you a bundle of your manifolds, and then you take a section of this bundle. And there are two conditions, so it's a differential two form, which is non-degenerate. This we have again, non-degenerate. So this is somehow a condition which is pointwise. So for every point, the form we see is going to generate. And then there's kind of a more kind of global condition and closed. So closed means that the differential of omega is 0. So we will see why closed is very important. So we'll see why it is important. So first, we will see it's important because one important property we want is on a symplectic manifold, you have kind of notion of time evolution whenever you have a Hamiltonian. And you want that this time evolution preserves the symplectic structure. So at some point we'll prove this, and in the proof it's very important to have this closeness assumption. And another spot where we'll see this condition is very important is when we define Poisson brackets. Poisson brackets, they have this Jacobi identity. Actually, you can prove that the Jacobi identity is actually equivalent to this form being closed. Okay, I'm not sure if everybody knows exactly what this differential means, so maybe let's do an example. Let's do some examples. Maybe even, I mean, this differential is defined for any kind of form. Here we have a 2 form, but let's define what's the differential of, for example, x dy. So this is a 1 form, say on R2. What is its differential? Differential means that you derive the function which is before, in front, like in all possible ways. Like here you derive it with respect to x and then with respect to y. So I derive this with respect to x, I get 1. And then somehow you should keep track of that you derive with respect to x. So dx, and you wedge with the differential you already have. And then you add up all these differentials. So you can also derive x with respect to y, well, then you get 0. Okay. If you do the same thing, another example with the differential of y dy, then if I derive it with respect to x, and I get 0. If I derive it with respect to y, I get 1. But then I get dy wedged to y, and actually wedged to y is 0. So the general rule is somehow you have kind of a function which depends on your variables, and then some differential stuff. I don't know, x1 wedge, I don't know, g1 wedge to p2, something like this, and the differential of this would be something like the sum of df dxi which is d1 d2 plus sum of df dp1 dp2. So you do kind of a differential, you compute the differential of f, and you wedge with that. So this actually, that's maybe actually even better. It's df differential wedge dx dp. Maybe that's okay. So the first remark is somehow that when we take 1 point, if I have omega x as an element, it's actually an element of this kind of, well, it's an element of omega 2 of txm. This is like a linear symplectic form. So this somehow makes the link between manifolds and what we've seen before. Just look at the point. The x is a point. In particular, the dimension of a manifold is the dimension of a tangent or cotangent fiber. So we know that m is necessarily of even dimension. Because if not, you will not get linear symplectic forms on these tangent spaces. Okay. Let's see some examples, or like it's more like a quiz. I will write some forms, and you will have to say whether they are symplectic or not. Just in order to check that you understand. Is it symplectic or not? first example will be 2 omega is x. Is this symplectic? So you see, like, now you have a dependence on the point.
It's not non-degenerate everywhere.
Yes.
Let's see.
Exactly. So it's not non-degenerate. Like, so maybe let's maybe first say what it means. So it means like omega, it depends on the point. So maybe to be very precise, I should actually put px here. So if I am, for example, at the point 2, 1, so I should feed it now with two vectors which actually are based at the point 2, 1. So I can, I don't know, feed it with vector v, p, vx, wp, wx. And then what you get is like the usual thing we have seen before, vp, wx, minus vx, wp. But now, since I'm at the point 2, 1, I have x equals 1, so I have a factor of 1. So if I'm at the point 2, 2, I would get a 2 here. So somehow it really varies. And so you see there is a problem whenever your x-coordinate is 0. If your x-coordinate is 0, you get just 0, and then it's not non-degenerate, it is degenerate. So this is not. Okay, what happens if I take still R2 and I take x squared plus p squared plus 1 dp dx? Symplectic, yes or no? So we should check. Where's the definition? Here. So, is it non-degenerate? Yes, because the factor here is always positive. And we should check whether it's closed. So it is closed simply for the following reason. We are on a two-dimensional manifold, and you have a 2 form, and if you take its exterior derivative, it will give you a 3 form, and the 3 form on a 2 manifold is always 0. So this is yes, this is yes, this is a symplectic form. Okay. Let's get 2 more examples. Okay, what do I have? Now on R4, omega equals x1 squared plus p1 squared plus 1, and then I think it's this standard one, p1 plus dx2 plus p2. Symplectic, yes or no? Why no?
With d on it.
What do we give 0 on both? Then first it depends only on x1 and p1.
So the parenthesis expression is just in front of the first.
Yes, it's just in front of the first one. Yes. Yes. Here's the one. Somehow x1, p1, and x2, p2, they don't see somehow each other. It's like a direct sum. Actually, this is, you can really see it as R2 plus R2. On this factor, I have like a standard symplectic form, and on this, I have kind of this symplectic form. And actually, like when you have 2 symplectic forms, you take like the direct sum, or maybe as manifolds, I would maybe more write it as a direct product. Then you can like get another symplectic form. So this is also a symplectic form, yes. Okay, and last example of the quiz, what happens if I take the same but with x2? x2 squared plus p2 squared plus 1 x p plus x2 p2. Symplectic, yes or no? Not closed. This is not right. What is d omega? So I should derive this with respect to x1, 0, with respect to p1 at 0, with respect to x2, 2 x2, and then I have dx2, wedge dx1, wedge dp1, and then I should derive it with respect to p2. It's dp2, wedge dx1. dp1, and this is constant, so this is 0, and this term, I mean, you can try to like rearrange them, but actually these two are different, so this is really non-zero. So it's not closed, so no. Okay? I think like having like very concrete in-coordinate examples might give you a feeling at least for what can happen, even if it does not really give intuition. Okay, so now let's get maybe some more physically meaningful examples. I mean, of course, R2n, the standard symplectic structure, will work simply because the standard symplectic structure is constant, and when you're constant, then the derivative is 0. Omega is t squared. So another example, which somehow always works, is when you take a surface, dimension 2, and an area form. Any kind of area form, this will work. An area form, like it gives you a signed area, so it's antisymmetric. It's not degenerate, it's like kind of definition of being an area form. And the closed condition is automatic, since the dimension is 2. If you differentiate a 2 form, you get a 3 form. Okay, and very important for physics, the third example is cotangent spaces, T star of n, for n any manifold. So I should maybe describe more, a little bit more detail what the symplectic form is. So what we would say is like omega is somehow dpi wedge dxi, but actually I should give a meaning to this object. So xi are coordinates on n, and pi are somehow linear coordinates. Linear coordinates on like the cotangent fibers on Tx star n. But how does it actually work? So there's actually a kind of simpler version. Like omega is a 2 form, but there's actually a 1 form. Like in physical terminology, it's kind of a potential. Actually, a symplectic potential. Symplectic potential. Theta, which is the sum of pi dxi. So this is actually a 1 form. T star n. So one form is something which takes a vector, well, a vector at every point, so actually a vector field, and spits out a number at each point. The number at each point is a function. So what you have to understand somehow here is the following. So what is actually the tangent space at a certain point, Tx, of T star n? Actually, it's not difficult to show that like the tangent space, since you have already kind of a linear direction, like right, you have n is like curved, but its cotangent direction is a linear subspace. So when you vary in this direction, you actually see again this cotangent space. You get actually the cotangent fiber at x, and you see the tangent space at n. Like tangent space, and somehow the cotangent direction is already a linear space. So you get this. So when you take a vector field here, so actually you can decompose your vector field into a cotangent thing and a tangent thing. And then what this formula actually just tells you is that in order to produce a function out of this vector field, you just take this linear function and you apply it to this vector. So theta of vector field, x, so x is now a vector field on T star n. So point by point, it's an element of the space. So actually you can decompose x into like kind of this x p plus xx And then theta of x is just apply xp, which is linear functional on xx. And this will produce your function. It's a bit difficult. I mean, it is really difficult to really understand what happens here, but like physically, kind of working in coordinates, somehow you really see kind of R2n. It's just that the coordinates x are actually curved coordinates. And sorry, and once you have theta, how do you get omega? Well, omega is d theta. Right, if you take the exterior derivative here, you should derive these with respect to x, but they're independent. And you should derive them with respect to p. The only non-trivial thing happening is when you derive pi with respect to itself, when you get 1 dpi.
Something. So is this decomposition of the tangent space of the cotangent space independent of the point P?
Yes, yeah, that's somehow the point, exactly. Yeah, it's like maybe I should draw a picture. You have like a curved space. This is n, and for every point you have a vector space, which is t. This point is x. This is t x star n. So a point in t star n. Point in t star n is, well, some couple x comma p. X is this x, and p is a point in this vector space. And now I want to vary this point, right? The tangent space is like, I want to vary this point. If I vary it in the direction of n, I actually just see the tangent space. If I vary it within this linear space, I just see this linear space that doesn't depend on p. Somehow how you get this kind of position. Other questions? Okay, I think these are really the three important examples. I mean, R2n is actually a particular case of this, right? It's T star R2n of Rn. Surfaces, it's kind of rare to really encounter surfaces, but these are like the main examples. So now we can speak about the symplectic gradient. Something I promised somehow is like one of the most important spin-offs of the theory is that whenever you have a symplectic structure function, you can actually produce this kind of canonically associated vector field. Symplectic gradient. Okay, so maybe you should recall the usual gradient. Usual gradient. So what's the usual gradient? So you have kind of a metric. You have a function. The gradient points in the direction where this function varies the most, right? Gradient f is a vector field pointing in the direction of, let's say, maximal change, maximal variation, maximal change. Like if you imagine, I don't know, like a height function. This is f, this is my manifold, f is defined on. Well, then if I have a point, then the gradient will point, well, either upwards or downwards, depends on the definition, but it will point in the direction of the steepest descent. And I don't know if you've actually really seen the definition, but how you would define it. So, I mean, you need, in order to define a gradient, you need a metric. So you have G, this is your metric. And the definition of the gradient f is that whenever you plug in this vector field in G, so G needs two vector fields, so if I take any other vector field, X is any vector field of my manifold, then the definition is it's minus df of X. So if you think about it, so df is the variation of f. df of x means the variation of f when I go into the direction defined by x. And so having this means that whenever, like in order to make this maximal, x should be aligned with gradient of f. And that's exactly somehow what's written here, right? Like, gradient gives you the direction of maximal variation. Somehow this is the way to put it in formulas. And now, like, once you have this formula, the definition for the symplectic gradient is actually the same. You just replace g by omega. Now you have symplectic manifold, and you have a function. Usually we'll take a smooth function. Then the symplectic gradient, I will typically write it either like this, symplectic gradient, or xf maybe sometimes, could be a little bit shorter, but this is the symplectic gradient. So what is it? Oh, it's the unique vector field which somehow satisfies this equation. Unique vector field satisfying omega of s squared f x equals minus d of x. This should be true for all x in vector fields. So somehow if you see this equation, it seems a bit like it's not very direct, this definition, right? It's like, it's kind of a property you want for this vector field to hold. So it's not completely obvious why it actually defines, like how would you actually write this symplectic gradient? Is that a question?
Exists, and why is it unique?
Why is it unique? Well, we will see. I mean, we can derive the formula for it, so we'll see. Yes?
Why is there a minus sign?
For convenience reasons. I mean, symplectic geometry is always covered with signs. I really stick to my convention. I mean, it's pretty. I mean, yeah, for the gradient, it depends whether you want. Like when you do gradient descent, do you descend gradient or minus gradient?
Minus gradient.
I think people would typically say that you do gradient descent with respect to minus gradient, and maybe this is why there's a minus sign here, but.
Doesn't it also have something to do with the orientation of the manifold?
I mean, you can put a plus sign here. It's just like later on there will be things. I mean, for example, I always say that this is the standard symplectic form, but you can also do dx dp, but then you get a minus sign somehow. Like, it's just to be coherent with everything. Yeah, it's not that important that there's a minus sign. Okay, maybe to see, like, first way to see why this is a good definition, you can go more conceptual. The second way is just to see the coordinates. The more conceptual is the following. Well, you have a function. There's a canonical way, actually, to produce a differential one form, which is just taking the differential. So this like function, and here you get a one form. But what we want is not a one form, we want a vector field. And actually, the symplectic form, like the fact that it's non-degenerate, it means actually that it gives you an isomorphism between like tangent spaces and cotangent spaces. So somehow it converts vector fields and one forms. So actually when you apply omega minus 1, you will convert actually the one form, minus 1 of df, and for some reason there's this minus sign. No? It converts the one form into a vector field. So you could actually say, I mean, you see it somehow in this formula, like you can apply omega inverse and then somehow forget about this x, and then you see that s gradient is equal to minus omega inverse df. But you have to understand, I mean, you have to think about what does it mean to like invert this kind of omega. But in coordinates, it's actually clear, because, I mean, in coordinates, omega is kind of a matrix, and then it's clear what it means to invert a matrix. So, now it's time to this definition. Okay, so in coordinates, that's maybe the other way to understand it. In coordinates, so S gradient F is some vector field, so it has an I component. I component is minus some omega inverse. Now I see it as a matrix. Okay. dx, where somehow xi are coordinates. Well, usually, actually, I would always say, well, there's x and p coordinates, and then the formula just becomes more complicated. But let's say that x1, x2, up to x2n. So let's do an example immediately. Yeah, let's do an example. Let's do R2 with dp wedge dx as symplectic form. So what is the symplectic gradient of any function? Let's call the function h. H is a function. R2. So what does this formula tell you? Well, first of all, we should write omega as a matrix. So as a matrix, it's 0, 1, minus 1, 0. You have like p and x, right? Like p with p is 0, x with x is 0, p with x is 1, p with x with p is minus 1. And then the inverse of this matrix, omega inverse, is minus 1, 0, 1, 0. And then what you should get is symplectic gradient of h. So you have an x component. So the x component should be minus the derivative with respect to p. So you have this 0 here. And an inverse. So probably, if my signs are correct, we should get minus. So as I said, we want to the x component here, then we should just get p derivative. So this is kind of the x direction, and you get the minus sign in the p direction. Does everybody more or less? I mean, have you seen these kind of partial derivatives as elements, like as vector fields? Yes? Okay. So on R2, you have two basic vector fields, the one pointing in the x direction, denoted by this partial derivative, actually for good reason, because a vector field is actually a derivation, and the vector field pointing constantly in the x direction is actually a partial derivative. And this gradient has kind of this form, and actually what you see, it is again, as before, somehow what we noticed, like it was like in the first observation we had, it is kind of this minus 1, 1, 0 times the gradient. The gradient of h would be derivative with respect to p, derivative with respect to x, and you get somehow this skew. So somehow this links to our very first example we saw, this kind of harmonic oscillator. And in general, when you have like a standard symplectic form, you just sum somehow these kind of contributions together. Okay. So there is a way to compute symplectic gradients and coordinates. There's a conceptual viewpoint, but somehow the important property is that whenever you have a function, you get a vector field, you can integrate, so you get a flow, and the important property is that this flow preserves the symplectic structure. What we produce is something which will not take us away from our somehow setup. So the flow generated by a symplectic gradient preserves and actually, well, the full proof, maybe I will just give you a feeling, like just a sketch how it goes. So So in Anton's lecture, we already saw a little bit like these kind of Lie derivatives and this Cartan magical formula. This is actually how we will do it. So we take f like a function. What do you want to show? You want to show that, well, this gives you a flow T. And what you want to show, like, preserving the symplectic structure means that whenever I pull back the symplectic form, it doesn't change anything. And if you will show, it will show that somehow the derivative of this is always 0. So we want to show that the derivative of t equals 0 of this is 0. And while doing it at t equals 0 or t any other value is actually pretty much the same, since the flow is kind of this kind of semigroup law. So this is kind of equivalent. And this part, maybe you recognize, this is the Lie derivative of the vector field applied to omega. And why is this good? Well, it's good because there is this magical formula for the Lie derivative. If you don't follow these technical parts, then you can wake up in 5 minutes, maybe even less. So we have like Cartan magical formula. Which tells you that when you do this Lie derivative of omega, it's actually the same as doing the following. It's taking the derivative, take the derivative of omega, so you get a 3 form, and you apply the vector field in the first instance, and then you have 2 other instances. And the second one is you plug first this vector field in, so now you have a 1 form, and you take the exterior derivative. This is this Cartan magical formula. Lie derivative, your Lie derivative preserves the fact that this is a 2 form. And what it says is like you first produce a 3 form and plug in the vector field to get it back as 2 form. Or you first plug in the vector field to get a 1 form, and then you apply this differential to get a 2 form again. Well, and now what happens? Well, this is 0 because omega is closed. And what happens with this? xf is the symplectic gradient. So you have omega symplectic gradient something. This actually is minus df something. And then you have d, and like 2 differentials, they cancel out. This is 0. Okay, and this is actually all. Somehow. But you see that it's very important to have this condition that omega is closed. That's what I said somehow. I mean, this is a property we really want. We say that phase space has a nice mathematical structure which is preserved under the physical evolution. Okay, so now we wake up again. Questions? Okay, then let's speak a bit about Poisson brackets. So a symplectic gradient, it allows to associate to a function a vector field. And now if I take 2 vector fields, sorry, 2 functions, well, I can produce 2 vector fields. Well, in 2 vector fields, I can feed them into the symplectic form, and then I get a new function. And that's actually all you need to define some bracket. So you take 2 functions on like a manifold with symplectic form, and then the definition of Poisson bracket. I think like usually in physics classes it's really just the definition is in coordinates, and that's just get the definition in coordinates, but it's really nice actually to see the definition, like this kind of symbol this thing, it will be a new function. It's again a function. And how is it defined? Well, you take the symplectic gradient of f, take the symplectic gradient of g, and you apply omega to it. So, I mean, this formula looks really nice, but as always in differential geometry, there's many information are hidden in this formula. For example, if I would want to write like what is actually this function evaluated at a point, let's call it just x, not x and p, it would be even worse. Well, where should I put all the x? Omega actually depends on the point, so you should write omega x. And then you have xf, which depends on x, and you have also xg, which depends on x. Yeah, I think that's all. We have 3 instances where actually x enters. So. Okay, so this is like a very nice object, and yeah, let's study a bit its properties and give an example, and then we will really see why it's very important. I mean, the physicists already know why it's important. It somehow gives how quantities like observables change over time. But before going there, let's give an example. Like, yeah, always the same, very basic example, dp wedge dx on R2. What's the Poisson bracket in this case? So if I have, like, we have seen somehow the formula somewhere over there. It's given by f dp dx minus df dx dp. If you do it the same for xg, it's the same. And then if you compute omega f and g, so what should we do? So we should apply dp dx to xf xg. And what is it? I mean, dp, it picks the p component of xf. So the p component of xf is minus, so this is minus df dx. And you should take the x component of g, it should be del g over the p. And then minus somehow everything reversed, but actually reversing, it's just changing x and it's just changing f and g, so minus minus is plus, df, dp, dg, dx. And that's somehow, I mean, this is kind of the canonical formula for the Poisson bracket, and that's also why people would typically say that the Poisson bracket is actually kind of a biderivation. It's actually del p wedge del x. Right? If you apply this to 2 functions, you should derive the first function with respect to p, second one with respect to x, and then exchange this with a minus sign. This is kind of the meaning, this is how people would say. And well, if we now go to R2n, you just sum over. Maybe you should just say, I mean, we define this object, the Poisson bracket, but you could actually define it in a just abstract way, saying how it behaves. Like the Poisson bracket has these 3 properties similar to the symplectic structure. So it's antisymmetric. Right? If I exchange f and g, then with a minus sign, it's bilinear. Actually, it's even better, right? It's like it is a derivation, so you have kind of a Leibniz rule. You have a Leibniz rule. Leibniz rule somehow says that FGH is FGH plus GH. And I have this Jacobi identity. The Jacobi identity is, like for mathematicians, it's like kind of the identity you would need in the Lie bracket. Actually, the Poisson bracket is a Lie bracket, but in addition, it has this Leibniz rule. And yeah, maybe I'll write it. So the Jacobi identity says the following: if you take these double brackets and you cyclically commute, like I have GH, commute it again, HFG, then you get 0. And what you can check as an exercise is the Jacobi identity of the Poisson bracket is actually equivalent to the symplectic form being closed. This is again like another good reason why the symplectic form should be closed. So again, actually, you can take this as a definition. You can say the Poisson bracket is something which is antisymmetric, bilinear, Leibniz rule, and Jacobi identity. And actually, it turns out that this definition would be slightly more general. Like from a symplectic structure, you can deduce a Poisson bracket, but there are Poisson brackets which cannot be deduced from symplectic structures. Typically, symplectic structure only exists in even dimension, but Poisson brackets also exist in all dimensions. Okay, so let's come to like maybe the most important property why we are so interested in Poisson brackets. Importance lies in the fact that Poisson bracket describes time, like time derivatives, like variations, time variations of observables. So the setting is as follows. You have a phase space, some symplectic manifold. You have a Hamiltonian. So this Hamiltonian gives you a flow. And the flow actually gives you a notion of time somehow. And now you take something you want to observe. I don't know, something you want to measure, like temperature, pressure, something. And you think about it, actually an observable is nothing but a function on your phase space. Right? The phase space is all possible states of your system. If you want to measure some new quantity, it just gives you one value for each state. So it's just a function on this phase space. So like you have an initial condition, you can measure your quantity, your observable, and then you want to know how this observable will actually change over time when you use your Hamiltonian to flow. And somehow it's simply given by the by the Poisson bracket. So how should I write this? I think I will just write this proposition. So I take H as a Hamiltonian. So that's actually really something which is kind of strange. The Hamiltonian is just any kind of function, but somehow you take this function as generating your flow. It gives you this flow, phi t. And then you take any other function, another function which is not the Hamiltonian, is typically called an observable. And then you want to understand the time derivative of f. Is the time derivative of f. Time meaning somehow that you flow along this, the flow given by this Hamiltonian, and this is given by the Poisson bracket of the Hamiltonian with your flow. Okay. earlier somebody asked for these minus signs. I mean, sometimes you see the other way around, but again, Poisson bracket is anti-symmetric, so if you see the other way around, it just means that at some point some minus sign has been defined differently. It's always about signs. I checked that I am, I hope, consistent in my signs. So this formula seems kind of innocent, but it can barely be overestimated, somehow, the importance of this formula. It really tells you that once you have kind of a Hamiltonian formulation of your physical system, you can define, I mean, you can know any variation of any function. And the proof is pretty simple. Proof. I mean, we have to understand what this actually means. So the time derivative, well, any kind of derivative is the differential of f is applied to some vector field. Which vector field? Well, the vector field giving the time evolution. The time evolution is given by the symplectic gradient of the Hamiltonian. So this somehow is actually the definition of its. And once you're there, you just apply definitions. So the definition of the symplectic gradient is that this is minus omega. So the minus sign is actually here, hf, right? Oh yeah, no. xh and xf, right? The definition of xf. Yes. Okay. So this is the definition of the symplectic gradient of f. It's something, when you plug it in the symplectic form and you plug in some other vector field, you get minus df. This. Okay. So now I can use the minus sign to switch these two, omega of xh, xf. And then I can use the definition of the Poisson bracket, which tells you that this is the Poisson bracket. Definition of the bracket. So actually it's kind of just using definitions. Definition of the derivative, definition of symplectic gradient, antisymmetry, definition. It seems like just using definitions should not give like a deep result, but it's actually surprising that somehow the definitions are the right ones, such that you get actually a deep result out of such a simple thing. So that's examples. Yeah, we always like the harmonic oscillator. Like come back to the harmonic oscillator. Harmonic oscillator. So remember h plus p squared over 2m plus kx squared over 2. So actually the basic variables are x and p. So you can actually apply this formula to any function. So let's apply it, let's say to x. What is x dot? So x dot is dx dt. By this formula, it's just h with x. So what's the Poisson bracket? The Poisson bracket, I mean, the harmonic oscillator is just R2 with the standard structure. So we have the standard Poisson bracket. So it will be, you derive p with respect, sorry, you derive h with respect to p, and x with respect to x, we get 1, minus derivative of h with respect to x and p, x with respect to p, so this gives you 0, which is this. And this is actually like kind of the first observation we had. And of course this is p over m. But somehow this equation does not give you something new. It just gives actually the definition of p. P is m x dot. But it doesn't matter, you can just apply it again. X dot dot. So this is h with x dot. X dot we just computed. It's 1 over m h with p. And again, you can apply this bracket, h with p, so it's the standard one. So this should give you minus 1 over m dh dx. And so dh dx is minus k over m x, right? Yes. And this is exactly Newton's law. You can also do P, H, P, then you get dH, dx. So somehow if you look at this and this line, you get kind of this first observation we started with, that time derivative is some kind of a skew gradient. If you look at this line, you see Newton's law. And if you take any kind of combination of x and p's, this will be any kind of observable. And then again, you can just apply this Poisson bracket to get it. This is a very, very simple example, right? Like you can imagine very complicated physical systems. Once you know the Hamiltonian, you can somehow derive all these variations. It's kind of citations stating that physics is about knowing, or like determining the Hamiltonian, all the rest is math. Okay, any questions for this? Quick. In the last 3 minutes, I just want to state the Darboux theorem.
Can I ask one question? So what are the sort of restrictions on the function h I can pick? Like can it only depend on x and p's, on x dots as p dots? Can it...
Like in this proposition, like h and f are just any functions. But I mean, what sometimes happens in physics that you say you have like some time dependence. This, I'm not sure if you can, I mean, you can build it in, but as it is now, it's not, I mean, h and f are not time dependent. So you have like one fixed phase space. Time evolution somehow is some flow on this phase space, but the phase space itself is not evolving somehow. You have a static view. Right? But I think you can build it in. Like you can say you take space times r, and r is somehow your time. More questions? Okay, so theorem. So again, like in order to state what does it mean that two symplectic structures are equivalent, somehow there is kind of a group, a symplectomorphism group. Space of diffeomorphisms which preserve the symplectic structure. So this is kind of the mathematical formulation, which means that up to coordinate change, you're not changing your symplectic structure. A group of symplectomorphisms. It's a very complicated group. I mean, it's infinite dimensional, and there's actually a nice subgroup. There's a nice subgroup which we call Hamiltonian diffeomorphisms. These are the diffeomorphisms which you can generate from a function. Well, you've seen the function gives you a flow. So if you say, well, I flow up to time 1, this gives you a diffeomorphism. We have seen that these kind of diffeomorphisms preserve symplectic structures. So they are symplectomorphisms. But actually it turns out that it's not all of them. There are symplectomorphisms which cannot be defined like this. So this is like time 1 flow of xh for some h. So we know that this is a subgroup of symplectomorphisms, but it's actually like, yeah, it's a discrete, how's it called, a normal subgroup. It's a normal subgroup, but they're not the same. Maybe for some examples, for some m's, they are the same. And then this kind of very strong Darboux theorem states that here is symplectic manifold, then take a point, manifold, then there is a neighborhood, open neighborhood, open open neighborhood of X, which is symplectomorphic. Which is symplectomorphic. Symplectomorphic. So R to M with its standard symplectic structure. In other words, it means that, like, especially physics, like in the physics viewpoint, you can choose coordinates around X such that the symplectic form is the standard one. Coordinates around X such that omega becomes the standard. Becomes omega. So again, it somehow tells you that, like in small neighborhoods, you always see the same things. Locally, nothing really interesting happens, but globally, you can have kind of strange, or, I don't know, like more complicated phenomena. In particular, for example, like some even dimension manifolds do not allow any symplectic structures. For example, if you take like spheres in even dimensions, like the 4th sphere, the 6th sphere, and so on, they are all not symplectic. You cannot even put a symplectic structure on them. Even if, of course, locally you can try. Locally you can like take R2n and its standard symplectic form. You can try to glue them together. It will never match somehow. So, yeah. So the global structure is very complicated. This may be like somehow the opening of the course. I mean, there's like a whole theory which is called symplectic topology, which would try to understand like which manifolds have symplectic structures, how many, understanding this group, getting invariants. This is kind of a whole very active research area. Another way to go is you can try to quantize symplectic structures, getting kind of a recipe to quantize. There are actually two kind of recipes. Either one is called deformation quantization, the other one is called geometric quantization. Especially in geometric quantization, you really use much the symplectic structure. For deformation quantization, you more have like Poisson brackets, which is a bit more general. And well, still kind of another, but very analogous world is symplectic structures are on even dimensional manifolds, but there's somehow a similar thing for odd dimensional manifolds, which is called a contact structure. And actually in physics, if you think about it, I mean, you have a phase space. It's always even dimensional because you have these conjugated variables. But once you fix your Hamiltonian, this is actually a good remark. I mean, the time derivative of the Hamiltonian by the formula is h with itself, bracket with itself, but the bracket is antisymmetric, so this is always 0. So this tells you that the Hamiltonian is always preserved. And typically, the Hamiltonian is the total energy, so you have energy conservation. So once you fix your Hamiltonian, you know actually you have this kind of hypersurface of like fixed energy, and you will never somehow go out of this hypersurface. So actually, why should we care about the whole phase space? We should actually just see this hypersurface. But this has no symplectic structure since it's of odd dimensions. And then you can kind of go into this contact world. There's something called the contact structure. And there are like contactomorphisms. I mean, this whole theory very similar to this one. We also have kind of the Darboux theorem. Well, so that's also a way you could go. But what we'll do in the next, like in the lecture on Friday, is we take kind of this theory, these symplectic manifolds, and we look what happens when you have symmetries. In physics, very often when you have a system with a lot of symmetries, actually it simplifies a lot. There's this notion of a reduced phase space. You have these conserved quantities appearing, and we will see how we can like formulate it very nicely.